Okay. All right, so now the next thing we want to consider is the following. Let's begin with the definition. Maybe let's do that definition. Okay, so let's say A is an n by n matrix. Okay, this definition is only for square matrices. A is called non-singular if the system AX equal to 0 has only the trivial solution or the zero solution. Okay. A is singular if it is not non-singular. i.e., the system AX equals to 0 has non-trivial solutions. Okay, so this is the notion that we can introduce to square matrices. Now, as you recall, we can also write A in its columns Okay. Then the system, hold on. We should also say X, the vector has components or entries x1 through xn. Then AX equals to 0 can also be written as x1a1 plus x2a2 plus xnan equaling 0. So now what is this? This, as we've seen already, is what we call a linear combination of a1 through an. Now, this has only solution x1 equaling x2 equaling all the way to 0 if and only if, by definition, this is actually a definition, if and only if the vectors a1 through an are linearly independent. Right? That's what we've seen before by the as definition of linear independence go. So therefore, we can formulate the following fact that the matrix A written in columns is non-singular if and only if the column vectors are linearly independent. Okay. Now let's do some examples. So let's say we are interested in this matrix and we want to decide whether it's non-singular or singular. Okay, according to the definition, what we need to do is to study the system x equal to 0. Okay, in this case, the system to be studied is 1, 3, 2, 4, x equal to 0, 0. So by now we've seen a lot of examples of linear systems. We know how to solve them. We form the augmented matrix and try to transform it. Okay, transform it into reduced row echelon form. And so here the leading one is already there. So we should just do R2 minus 3R1. That'll be 1, 2, 0. 3R1, 3 minus 3, 0. 4 minus 2, 4 minus 6 minus 2. This is still 0. Then you can do, say, R1 plus R2 and followed by dividing R2 by negative 2. And that'll bring the matrix down to the reduced row echelon form. Okay. And the reduced row echelon form is being given like this. You see that the only solution is x equals to 0, 0. Okay, so the matrix here is non-singular. All right. Let's look at another example. Say this one. Again, the question is whether it is non-singular or singular. So for that matter, we form the system, or we can even skip that step and get on with writing the augmented matrix. 1, 2, 2, 4, 0, 0. And what we're gonna do, we're gonna try to bring it to reduced row echelon form. Again, you already have a leading one in the first row. So you're gonna do R2 minus 2R1. 1, 2, 0. But that turns the entire row 2 into a 0 row. So therefore, this is the place to stop. And you see that now you only have one variable is determined, meaning there's only one equation, x1 plus 2x2 equals to 0, which just means that x1 is negative 2x2, which means x, being x1, x2, is equal to minus 2x2, x2. So you can also write this as x2 times the vector minus 2, 1. So infinitely many solutions. So the matrix is singular. Okay. So in general, this is, this is sort of the way to decide, or one way for now, to decide whether a given square matrix is singular or non-singular. Now, we're going to be interested in the following result about non-singular matrices. So state this as a theorem that A be an n by n matrix. Then the equation or the system Ax equals to B has a unique solution for every n by 1 vector or matrix. So n by 1 let's call it column vector, just to be clear. Vector B. And the statement I'm making on one hand is that the system Ax equals to B has a unique solution for any given vector B. And this is equivalent, or if and only if A is non-singular. Okay. So let's prove this. So this theorem is about two statements being equivalent. The statements are encircled here. So we have to consider two implications. The forward implication is saying that if the system X equals to B has a unique solution for every B, then A is non-singular. If we assume that statement, and we can certainly take B to be the zero vector, then the assumption implies that Ax equals to 0 has a unique solution, necessarily the zero solution. So A is non-singular by definition. Okay. This one is easy. The other way around is not as easy. So suppose A is non-singular, then we want to show let's first of all pick any vector. Let's say B is an n-dimensional column vector. We want to show that the system Ax equals to B has a unique solution. Okay. There are two things to do. First of all, the system has a solution. then secondly, that solution is unique. Okay. So to show that it has a unique solution, there we do this in two parts. So there's the existence of solution. No. So here goes. We can again write A as column vectors, as a collection of column vectors, right? Then we have A1 through AN and B n-dimensional vectors. So we have these guys, we have these n-dimensional vectors. N-dimensional vectors. How many do we have? There are n plus 1 of them, right? A1 through AN together with a B. And n plus 1 is surely bigger than n. So you have more vectors than you have n. So we know from the previous lecture that these vectors A1 through AN, B are linearly dependent. All right. Which means what? Which means, by definition, there exists A1 through AN plus 1 numbers such that A1 plus AN plus AN plus 1 B equals to 0. Okay. Now, make the following observation. That the number n plus 1 is not 0. Okay. Because if n plus 1 were 0, the above, this one, equation becomes A1 n1 plus AN equal to 0. Now I should have mentioned that because A1 through AN and B together are linearly dependent, these coefficients A1 through AN plus 1 are not all 0. Right? That's one thing about linear dependence. Now we want to argue that AN plus 1 in particular is not 0. For that, we assume that if AN plus 1 were 0, then the equation gets simplified into this. This is a linear combination of A1 through AN equaling 0. Now, because A is non-singular, by assumption, we have, as we've seen really above, these vectors A1 through AN are linearly independent. which by definition means that these coefficients here, the coefficients in this equation, a1 through an are all 0. Means that a1 through an are all 0. Now, but I've assumed already that an plus 1 is 0, and if I also get a1 through an all 0, then all these a's are 0. But I'm supposed to have some of them not 0. And that's a contradiction. So it cannot be the case that an plus 1 is 0. So an plus 1 is not 0. Very good. Okay, then what? Once you have a non-zero number, you can do the following. You can divide by a non-zero number, right? So going back to this equation, this linear combination equaling 0, if we divide this equation by negative n plus 1 and move one term to the right, we get a1 on negative an plus 1, a1 plus an on negative an plus 1, an equaling b. Okay. Now, this is saying this is saying that the matrix A times the column vector minus a1 on, not that, a1 on minus an plus 1, a2 on minus an plus 1, an on minus an plus 1, this is equal to b. So we get a solution. Okay. That's the existence of solutions. Now we figure out the uniqueness of solutions. Okay, so how do we do that? I mean, if you want to show uniqueness, one straightforward way for doing that would be to say, suppose you have two solutions. Let's say u and v are both solutions to ax equals b. In other words, i.e. au is b, av is b. Okay. Then let's consider a applied to u minus v. This is by the property of matrix multiplication, au minus av. Now au is b, av is also b, so that is 0. So we get, what is this? So a times u minus v is 0. This means u minus v is a solution to the system, homogeneous system AX equals to 0, because we assume that A is non-singular, the system AX equals to 0 has only the 0 solution. Okay, so we must have that U minus V equals to 0, which is the same thing as saying U equals V. Okay, so what we've achieved here is that if you have two solutions, U and V, they must actually be the same. So there can only be one solution. All right. So that's about non-singular or singular matrices. Now let's move on to the next discussion, which we can motivate a bit as follows. Let's say you have AX equals to B, an equation of numbers. To solve it, we suppose that A is not 0, right? I should mention that we should mention that AX is the unknown, right? If A is 0 and the left-hand side is 0, then 0 equals to B is not much of an equation unless B is 0. So we assume that A is not 0. Then we can solve it by multiplying both sides by A inverse, which is the same thing as dividing both sides by A. Now, A inverse times A is A inverse times A times X, and that is 1 times X, which is X. So if you do this, you get X equals to A inverse B. Now, what we have been looking at matrix systems, matrix equations, or systems of linear equations, AX equals to B, where A is a size n by n matrix. Now, it would be nice if we can do what we've done before, namely multiplying by A inverse, multiplying by the inverse of A. So to make sense of this, you first of all need to, explain what do you mean, what inverse of A should be. And then go from there. And that's, for that matter, we introduce a definition. Okay, the definition is the following. So let's say A is an n by n matrix. Okay, A is invertible. If there exists another n by n matrix, which we judiciously denote A inverse, such that A times A inverse is equal to the n by n size identity matrix, which is also equal to A inverse A. So this is the n by n identity matrix. Okay, so this is the requirement for a square matrix being invertible. And if this happens, such A inverse is called an A inverse or n inverse of A. Okay. Now, the first remark is for more or less simple, is that if A is invertible, then its inverse is unique. Okay. So how do you want to do that? So suppose to see this, let's suppose you have two of them. Suppose both B and C are inverses of A. Then what happens? Then the following happens. You can see that B is equal to B times the identity, and the identity is B. The identity is also equal to A times C, because C is A inverse. Now, associativity allows you to group the first two product together first. So B times AC is BA times C. Now because B is also an inverse of A, BA is identity. Now identity times C is C. So that's it. This shows that two inverses of A must actually be the same. Okay. Now let's think about some examples. Say my matrix A is 1, 2, 3, 4. And I'm interested in whether it is invertible or not. So how am I supposed to approach this problem? Let's just suppose that it has an inverse, say A, B, C, D. Then it has to satisfy this property, right? A times that equals to the identity matrix of size 2 by 2. And that means what? 1, 2, 3, 4, A, B, C, D equals to 1, 0, 0, 1. Now, if you compute this, you get A plus 2C, B plus 2D, 3A plus 4C, 3D, B plus 4D equaling 1, 0, 0, 1. So you now have four unknowns, A, B, C, and D, and they are given by two systems. One is this, which gives you A and C. The other is this, B plus 2D, 3B plus 4D, which gives you B and D. Now, we've seen already how to solve systems of linear equations. So we're just going to do that and decide that A and C are going to be equal to, it will turn out that A and C are equal to these values respectively. And B plus 2D goes to 0, 3B plus 4D equaling 1. And this will give us B equals to 1, D equals to minus a half. Yes. Okay, so what we've seen is that this product is exactly as required for being the inverse of A. You can also check by hand that this product in a different order is also equal to the identity matrix. So indeed, A inverse exists in this case, and it is equal to that. Okay. Now, let's consider another example in this manner. So suppose A is 1, 2, 3, 6, and we want to know whether it's invertible or not. So for that matter, we assume that the inverse looks like this, and we want to consider whether this equation is possible. Okay. Not sure what's happening here. Okay, and this equation is 1, 2, 3, 6, A, B, C, D equaling 1, 0, 0, 1. So that's the same as A plus 2C, 3A plus 6C, B plus 2D, 3B plus 6D equaling 1, 0, 0, 1. Okay, now for this equation to hold, you need a plus 2c to equal to 1, a plus 2c to equal to 1, and you need 3a plus 6c to equal to 0. 3a plus 6c to equal to 0. You need both to happen at the same time, but this is not possible. Because 3a plus 6c is 3 times a plus 2c. If a plus 2c were equal to 1, 3a plus 6c should be 3, not 0. Okay? So, therefore, you cannot find a, b, c, d. You cannot find a, b, c, d for this equation to hold. So, a is not invertible. Okay. Now we let's spend some time on general discussion. Remember, our motivation for considering invertible matrices were to solve linear systems as if they were equations of numbers. So indeed, let's say you have a system AX equals to B with A being n by n matrix, invertible. Okay, then you can do the following. You can multiply both sides by A inverse from the left, and the left hand side becomes A inverse times AX. For that, you can rewrite as A inverse A times X, which is A inverse A by requirement being the identity times X, which is therefore X. So this shows that X is A inverse B. Easy. So you see indeed that if you have a system AX equals to B with A being an invertible n by n matrix, then X is easily computed as a matrix product. X is A inverse B. So therefore, for the purpose of solving systems like these, you may also want to consider the question of computing A inverse. Okay. Now we can launch a more general discussion about existence of A inverses. So, and the approach is going to be somewhat computational. Let's say A is an n by n matrix. Okay. And if A is invertible, then there is an n by n matrix B such that AB is equal to the identity matrix. right? This is one. B is supposed to be, B is then the inverse of A. And this equation here is, this equation here is one of the required properties of being an inverse. Okay. Now, we can write, not that. We write B in column vectors. Also, note that the identity matrix I, if you write it in column vectors, if you, first of all, the identity matrix I looks like these, right? It's 1, 0, so on, 0, 1, 0, so on, 0, 0, 1, 0, so on, 1, 0, 0. Now, if you look at, if you look at the columns of these guys, this identity matrix, you recognize them because the first column is what we call E1, the unit vector E1. Second column is the unit vector E2. The third is unit vector E3, and like so on. So for this reason, if you write the identity matrix in column form, it is this guy, E1 through En. So therefore, the system or the equation AB equals to I can also be expressed as follows. A times the columns B1, B2, Bn equals to E1, E2, En, or in other words, the following. You see, if you look at this equation, and when you execute the matrix product, you really are getting n equations, one for each column. So the equations are AB1 equals to E1, AB2 equals to E2, so on, ABN equals to En. So you have now, if you want to find B1 through Bn, you want to solve all this distance together, and this distance have a common feature. That is, the coefficient matrix is A. Okay. So notice, so to find B, i.e. finding B1 through Bn, we need to solve all these systems above. And the above has n systems. Right, and just like we said, the inverse of A, if existed, is unique. So if we are to find the inverse, we want the unique solution to each system. Right, so we certainly hoped, we've seen that when A is non-singular, these systems have unique solutions. Okay, so therefore, if A is non-singular, these systems have solutions uniquely. Therefore, you have a chance of finding the inverse of A, that is, A is invertible. On the other hand, we've already seen, as above, that when you have AX equals to B a system, with A being invertible, then the system has a unique solution. And this, by our definition, means that A is non-singular. So we can almost convince ourselves that being non-singular is the same as being invertible, which is true. But for the proof of that, we need the following lemma. Okay, let's say PQ are n by n matrices. If either P or Q is singular, then so is PQ. Okay, that is, if you have two square matrices, at least if one of them is singular, then the product is singular. So let's prove this. Suppose Q is singular. What does that mean? That means some system, or that means the homogeneous system associated to Q has a non-zero solution. Right? The homogeneous system Qx1 equals to 0, Qx equals to 0 has a non-zero solution. X1 not equal to 0. Then PQ, the system PQX equals to 0 has a non-zero solution. X equals to X1, because PQX1 is PQX1, which is P0 by our choice of X1, which is 0. Okay, now have the system PQX equaling 0 has a non-zero solution. That means PQ is singular. Okay. Suppose now let's suppose Q is non-singular, just to make it interesting. I mean, we know the statement is true if Q is singular. So suppose Q is non-singular and P is singular. Then P being singular means that there exists say x2 not equal to 0 such that px2 is 0. Right? The system associated to P has a non-zero solution called x2. Now, Q is non-singular, so the system Qx equals to x2 has a unique solution. Say x equals to x3. Then PQ. Then we want to consider the system PQX equal to 0 again, as before we proceed, we should observe that x3 here is not 0 because x2 is not. Okay, then the system PQX equals to 0 has a unique solution. Not a unique solution, has a non-zero solution. X equals to x3 because PQ times x3 is PQX3, which is PX2, which is 0. So PQ is again non-singular, singular. Okay. Now, with this lemma in hand, and we'll come back to using it later, we can now state, but before that, we can now state the following theorem, which says that for an n by n matrix A, A is non-singular if and only if it's invertible, or A is invertible if and only if A is non-singular. Proof. We've seen how the forward implication works. If A is invertible, then the system AX equals to B has a unique solution. That is X equals to A inverse B, as we've calculated above. So A is non-singular. Now, conversely, if A is non-singular, then the systems that we've considered before, A B1 equaling E1, A B2 equaling E2, and so on, A Bn equaling En, all have unique solutions. This gives the n by n matrix B equaling B1, B2, and so on, with the property that AB is the identity matrix. Okay, so we want B to be A inverse, right? But for this to hold, we also need to show that BA is the identity matrix. Okay. Now for this we make the following observation. Because AB is I, B is also non-singular. A is assumed non-singular, right? And B is also non-singular. Okay. How do you see that? If we consider a system Bx equals to C, then I can solve it, right? By multiplying by A from the left, I get to solve it like this. This is AB times X. This which is I and X, which is X. So the system, any system associated to B thus has a unique solution. So B is non-singular. And the process uses this property that AB is IN. Okay. Now B is non-singular, right? So there exists C such that BC is identity. Okay. Now what? Now we can do this. Let's say A is A times identity. Identity is equal to BC. Now associativity tells you that you can write this as AB times C. AB is also identity. So you get C. So A is equal to C. Hence BC, BA is equal to BC, equaling the identity, which is what we want to prove. Okay. All right. So you may ask where we use the lemma. The lemma was to say that if you have two matrices, one of them is singular, then the product is singular. So conversely, so if PQ is non-singular, then P and Q are non-singular by contrapositive. And that's where we use this lemma. Because we have AB here, the product is the identity, which is non-singular. Both A and B must be non-singular. We could either use the lemma for this statement, or we could just check it. Okay, that's the end of this lecture.